So, good morning.
Oh, good morning.
The fact that it's Friday. So, I'm Viviana Coviva. I'm on the faculty at CUNY. Mostly, like science-wise, I mostly study galaxies and distant galaxies. And so nowadays, a lot of the things that we do are a bit more oriented towards machine learning methods. But for a long time, I've used Markov Chain Monte Carlo to do spectral energy distribution testing, so infer the properties of galaxies. And so this is what we are going to talk about today. I think it's going to be a pretty simple class. We'll have like a very short lecture just to remind ourselves so what MCMC does, what it's useful for, like a little bit of terminology and like the different pieces. But really, I feel like we'll switch to coding, and I think most of you seem to be comfortable at least from the class that I attended about Bayesian hierarchical methods with Fini, with coding, with Jupyter notebooks. But I think it's nice if at least one time one sees how simple it is to actually build the Markov Chain Monte Carlo algorithm from scratch. And so we'll try to get there. It's really like a few lines of code. And then I'll just want to show you like a few simple tests that you do. Like a lot of MCMC is really common sense, right? Like we expect our algorithm to behave in a certain way. We can think about it, just, using basic science method, what do I expect to happen if things are going well? And I feel like for a lot of problems, this is sufficient. And then we'll see, hopefully we'll get to see what happens when things break, and how you can realize that things are breaking, and like what are other possibilities. Sounds good? Okay, so how many of you have used MCMC? Okay, I would expect a bunch. How many of you have written an MCMC algorithm? Okay, a few. So if you have, when the time comes of, like let's trying, feel free to sort of walk around the room and help others who may have not, right? Because, in some sense, if you have done it before, this may be like a redundant exercise, but I think it's very helpful if you want to sort of like put your ability and experience to the service of others who are trying for the first time. Okay, so I'm just going to go ahead. Since it's Markov Chain Monte Carlo, let's figure out what each one of these things means. So Markov, like a Markov process, is a process in which each step only depends on the current location. So in other words, like a Markov chain is a chain in which at each step, the chain has no memory of what happened before. But basically, when you are in one place, like your current location and the knowledge of where to go next is the only things that you use. A chain is just a sequence of steps, often in parameter space if you're doing inference, which is what we'll be doing. And Monte Carlo just means that we use random numbers in a way. But I figure, hey, it's good to know, why it's called MCMC. So let me switch these center views so that I can have a clue what comes next. Okay, all right, so I'm not going to try to be super general, so I'm just telling you. Let's assume that we are using MCMC somehow because we want to do inference on some parameters. Now we have some data, we have some models, our models depend on some parameters. This is what we want to measure. And so in general, if we are thinking in Bayesian terms, what you want to do is to get a sense of your posterior, the probability density functions, and so this basically will tell you what you can expect about your parameters given the data that you have. And Bayes' theorem tells you that you can split this in the product of three things. The first thing is some constant. I think in Astro we tend to call it evidence, some people call it marginal likelihood. Basically, it's an integration constant. It gives you the total volume of the likelihood in parameter space. But for us, it's actually not essential, so we're going to set it aside. And MCMC is not a great way to measure it anyway. Here, you have the likelihood. So the likelihood is the piece that tells you if you were to know the parameters, how would your data look like? And so this is the piece that we put in. And then the other pieces is a piece that only depends on the parameters, so there is no data here. And this is called the priors. And this basically is what summarizes your beliefs about the parameters that you're measuring. And so in general, these priors may be more or less informative, but it's a good idea if they are a regular function, which means that they are finite or so-called proper. You don't want something that has like, no extension, at least you want to give a range. They may be flat if you feel like, okay, I believe that this is the range of possible interest, but I don't want to give more information about how I expect those to be distributed. But in other cases, you may actually want to put in information about what this is, right? Knowing, for example, that some particular regions of parameter space are considered to be more likely because you have knowledge about that. So that's fair. Now, in general, this seems to indicate that what we want to know is the posterior. However, when you're doing inference, in many cases, you're not really interested in knowing the full probability distribution function in many dimensions. What you want to be able to say is, how do my parameters look like? And so you want to do statistics on your parameters. You want to say, okay, this is the range. These are the credible intervals. This is like the shape of their probability distribution. And if you have your PDF in many dimensions, well, this is just in 2 dimensions, to obtain these constraints, what you're supposed to do is to integrate the posterior density in many dimensions, as many dimensions as the dimension of your parameter space. Or if you want, for example, to see the distribution only in 1D, you will integrate in every dimension other than the dimensions that you're interested in. Now this may not seem particularly difficult, right? If you look at something which is as regular as a 2D Gaussian, right? This is something that is easy to integrate. But most often, posterior functions have a shape that is not regular. For example, my favorite, a giraffe. This is something in which you can see that, like the peak of the probability is here, but the vast majority of the volume is here. And so this is, like perhaps not the most realistic, but a reminder that, ordinary posteriors don't look like Gaussians, and so slicing is not the same as integrating. The mode is not the same of the mean. And so because of that, integration is usually not an easy task. And that's where MCMC can be of help. So for example, say that even if you're not even looking at distributions, you want to figure out what the expectation value of a certain parameter is, what we call the mean. So what we are supposed to do, I guess I would use this. I'm always so afraid of pushing the wrong button. Anyway, so say here, you have like a bunch of parameters. Since I used to do spectral energy distribution fitting of galaxies, usually my parameters were things like, the age, the mass of the galaxy, how much dust there is, the redshift, the metallicity, tau, some sort of like, time scale associated to star formation. And so in order to say, okay, I want to find the expectation value of age, I will have to take my posteriors and to integrate, sorry, this is a prior, and to integrate, and this is a posterior, and to integrate in all the dimensions that I have. And typically these integrals are quite painful. So what if, rather than having to do the integral, you had the series of points that were distributed exactly identical to your posterior? And now the next integral becomes a sum. And sums are easy to do. And so if you have this series of points, which we are calling Ri, basically all you will have to do to compute the same integral will be to sum the value of your function, my function f for me was age, at all the location of the points. And so this is really, I feel like, the magic of MCMC. It's not, a method that allows you to do things that were impossible to do before. It's just a way, at least, like in my view, of making that process a lot simpler. Now, of course, the issue is you want this series of points that is distributed just like the posterior because you want to do the magical chain. how are you going to go about finding them? And so MCMC creates this prescription so that you can obtain the points that are distributed like a posterior, so you can turn all the integrals that you have to do into sums. And by the way, all, typically all the statistics that we do about parameters, whether we are looking at the expectation value, whether we are looking at the credible intervals, whether we want to have like the full probability distributions in parameter space, you can do all of these with appropriate sums. So how are you going to do it? So the trick is that we are going to explore the parameter space, I don't want to say not randomly because it is somewhat randomly. Let's say we have like a biased random walk, and the property that we are going to try to enforce is the fact that the density of the points that you visit is proportional to the posterior distribution function. And so this is like where the magic begins, right? So basically, if you are in an area where your posterior is large, so that occupies like a large volume in parameter space, you're going to spend a lot of time there. And this will be reflected in the sum, the fact that you're going to sum multiple times over these points that are all close by. This is the same thing as having a large volume in integration. And vice versa, you will also spend time in areas of the parameter space where the volume of the posterior is low, but you're just going to spend less time there. And so the amount of times that you make the sum over those points will be lower. And if things work out fine, which means if your set of points is distributed exactly like the posterior, this will ensure that you have like a small error between doing the integrals in the full posterior dimensionality and doing that sum of points. So, all that there is about MCMC is that it's actually a fairly simple prescription to obtain this magical property. So far, so good? Okay. So the simplest implementation of this is something called the Metropolis Algorithm. I wanted to put all the animations, but I got too lazy, so you get it all of this at once. But this is how it works. So you are at any location in parameter space, that's called the x0, and you compute the posterior there, which will be the product of your likelihood and your prior at that point. Okay? Then you have to jump somewhere else. Right, the whole idea is that you're exploring, and so you can't stay in one point. You're like, okay, I'm in this point, I'm going to go in that point. And we can talk, actually we will talk about how you go from one point to the other, but in general what you use is something called the proposal density. Like there are simple ways of moving from one place to the next. You can just take a random step of random size in a random direction. And that's actually okay, not terrible. But there are, somewhat better ways of deciding where you should be going and, like how far away. Anyway, let's say that with one of these prescriptions, you go to a different place. Let's call it x1. Now you can also compute the posterior there. And then you compare the two. Okay? And let's say, like either you will find that the posterior in the new location is higher, or you will find that it's lower. Well, if it's higher, there are no doubts you're going to accept your step. And this is because, in general, you want to be moving towards the interesting regions of parameter space, which are the ones where the posterior is large. Right? So you're like walking around and it's sort of like doing like a vague biased random walk towards the interesting region. However, even if the posterior at the new location is lower, you can't always discard this point, because otherwise this will become some sort of gradient descent, where like once you are at the top of your posterior, there's no way for you to move. And so this is like an optimizer and not a sampler, while MCMC is very much a sampler. So instead, what you will do is that you will still, in some cases, accept a posterior with lower probability, but you will accept it with a probability which is proportional, actually not even proportional, which is equal to the ratio of the posterior values between the new point and the old point. So let's say that you found the new point and the posterior ratio of new point divided by old point is 0.8. This means that 80% of the times you will accept that point, and 20% of the time you would reject that point. Right? And so what's in code, this is typically implemented by generating a random number between 0 and 1. And so you will accept the step if the ratio of the posteriors is larger than that random number, and you will reject it otherwise, which is the same of implementing, like, let me accept it 80% of the time. Okay, once you have that, as I mentioned, you generate your random number. If the posterior is larger than your random number, you will accept it, otherwise you will reject it. And the important thing is that at the end, no matter what, you will write a new step to the chain, right? The new step will be either the new point, if you have accepted, or the old point again. And this is what ensures that you're spending a lot of time in regions that have like a large volume of the posterior, because you may end up moving with a low probability from that area, which means that you will have like a higher density in that region. Make sense? Okay. So what's good about MCMC? Well, I think I have two things. One is that it's easy. So we already mentioned that basically all you have to do to do statistics is to count points. And so we've seen what happens when you're just calculating like the mean value or expectation value of a point. But say that typically what you're interested in quoting some sort of measurement. You can check, typically you won't have the mode, but you can have the mean, you can have the median, we can talk about it. But then we also want to mention a range, something that we call credible intervals, right? For example, the 68% region, 95% region, which means that you believe that approximately 2/3 of the time, or approximately 95% of the time, 19 times out of 20, your true value of a parameter will lie within a certain interval. And so doing these things, you could do it, again, in many ways. You don't need MCMC to do that, right? You could assume that your posterior is Gaussian, and so you can compute your 68, 95% confidence level as 1 or 2 sigma deviation. This is very tempting, but it's wrong. It actually almost never works. You could do the painful thing, which is, like look at your posteriors, figure out how it looks like, for example, by gridding, integrating in many dimensions. This is correct, but it's not so fun. Or you can count the points that lie within 68, 95% of the points sampled by your chain. You can see how much easier that is. Now, I think one thing to keep in mind is that it's very easy. For example, I'm looking in one dimension. I will have like a whole bunch of independent samples. So let's say that I have thousands of them, just make a number. You can find the interval that contains 680 of them. That's your 68% credible interval. So very easy. How should I go though? The trick here is that I feel like the most correct thing to do is that you move sort of like from the right and from the left and towards the center, rather than being anchored to something which is in the middle, like a mean or mean value. I mean, you can do it from the mean, of course, but the idea is like I feel like the most fair way is like integrating from 0 to 16%, integrating from 100 towards 84 percentile, and what you have in the middle is your 68% credible interval. And you can do like the annual thing for like 95 or really like any confidence level that you would like to do. Quite easy. So this I feel like is winner property of MCMC, how easy it makes for you to do statistics. There is another thing which is actually efficiency. And perhaps this is, you guys would not even like think about it, but when I started doing these things, which was over 10 years ago, a lot of times, like the way to do statistics, even over a large parameter space, was to do some sort of gridding, right? Which means that you have the space defined by your prior, which is typically a large space. This is only 2, but typically you have more dimensions than this. Which means that the interesting region, the region where the posterior has like a decent volume, is quite small compared by the range defined by your prior, which is like everywhere where your posterior could be. So if you were to cover the space with a grid, right, and then compute the posteriors everywhere to get the sense, this would actually mean that you spend a lot of time working in non-interesting regions. And so it's a wasteful way of exploring. It's correct, but it's just like not efficient. And so one of the things that I feel like is convenient about MCMC is that you can start wherever, right? Typically, actually, you want to start with many random locations, and you will start sampling the parameter space going back and forth. But then, once you sort of like get close to your interesting region, you will recognize that, and then most of your time after that will be spent around there. And this means that even if you don't know, which of course you expect that you don't know, where the interesting region is, you can always find it, and then you'll spend most of your computational time will be spent, which is a good thing. Now, things that are not so great. Well, I feel like the main one is the fact that you can never know really if you have time. So, as we mentioned, the whole architecture of MCMC relies on this key property, which is the fact that your samples are distributed like your posterior. Like, if this is true, everything works beautiful. How can you know that this is true? And the problem is that you don't really. You have a bunch of necessary conditions. You have necessary conditions on how you move from one place to the next, something called detailed balance that we haven't quite looked at, but you can read in the paper. And then you know that some things needs to be true, but there is no sufficient condition. And so this is the thing that it means that, that's why I feel like, common sense, looking for things, sanity checks. These are things that you will use every day when you use MCMC, because there is no single thing that you can test to make sure that it is true that your set of samples is distributed like the posterior. So the most intuitive thing, which is also the most important, is the fact that the chain is supposed to evolve towards a stationary distribution, which means basically that at some point, once you've got the right answer, you don't move away from this. And so as you continue sampling, you're just basically building more numerous samples, but are always drawn from the same distribution, which is the posterior. So in some sense, what you want is looking at the convergence of your chain. You know that it's bound to happen, that if you run the chains for long enough, with the right conditions, they will eventually evolve towards the correct posterior density function. But you cannot wait forever. So what you want to try and do is basically check, if I continue running this chain, do the results change? Do the results change? And the other thing, which is sometimes even more useful, if I run many chains, probably starting in different areas of parameter space, do I get always the same results? These are things that your algorithm needs to pass. Still not a guarantee that that property is verified, but it's something that in general is quite helpful. And in many cases, if things are failing, you could figure out, you could find out from these kind of tests. All good? Okay. And things that are, not good and bad, but in general, as you can imagine, so what we're looking at and also what we will be coding with is the simplest algorithm, which is Metropolis. Now, this is very easy, as we mentioned. There are several things that we can do to improve the efficiency. So efficiency is something different because, in general, you want your sampling to be efficient, which means that you need to do two things. You need to make sure that you spend time in the interesting region, because you don't want to waste time in like faraway regions that nobody cares about because the posterior is very low. But at the same time, you want good mixing, which means that you need mobility of your chain. The problem is, especially if your posterior, rather than being a nice and beautiful Gaussian all in one location, what if it's something with like multiple peaks perhaps separated by valleys, like the nightmare of every sampler. And so in some sense, you need your chain to also have enough mobility to possibly get in there, rather than being stuck in its own local maximum, for example. So you can do this with Metropolis hastings. So, the simplest thing to do is that you change that proposal density. Basically, you change the directions, doesn't matter so much, but the step that you take in different directions to move to a new point. And one of the simplest metrics to optimize is the acceptance rate. The acceptance rate means how often, as you move to a new location, you accept your new step. So you can imagine that if I have a tiny proposal density, what will happen to my acceptance rate? It will be high or low? Tiny step? Will I accept many steps? No? So if I'm in a step, it means that the user is quite good. if I take tiny steps, I'm quite likely be in a place where my current posterior and the new posteriors are very similar, which means that if I'm going up, I always accept. But even if I'm going down in posteriors, because these 2 points are so close, it means that probably, like my new posteriors may be like 90% of my old posteriors, which means that in 90% of the cases, I will accept the new state. So having a tiny proposal density gives you a high acceptance rate. In fact, this is like a good debugging technique, checking that as you make the proposal density smaller, your acceptance rate goes up. And you can also, to increase mobility, you can make your proposal density larger, which means that you take bigger steps. This typically makes your acceptance rate go lower because, of course, you are more likely to move away from the high posterior region. But at the same time, it ensures that you are exploring more widely. And so it helps a bit with that. And so people have different ideas, but typically your ideal acceptance rate wants to be between 1/4 and 1/2, so say 30%-ish. And so this is, one way that you can sort of trade off between, like exploring and being efficient. More in general, and this is actually what Hope and Dan argue in the paper that I don't know if you guys took a look at. Their idea is that the single most indicative metric of the efficiency of a sampler is something called the autocorrelation time. The autocorrelation time is basically the separation measured in steps of the chain, after which you have independent samples. So you can imagine that if you have your sequence of steps, and you take your sequence, and then you take your sequence shifted by 1 step. You measure the correlation between these 2 arrays. It would be very high, right? At lag 0, it would be exactly 1, because you're looking at the same array. If you shift your arrays by 1, it will probably still be quite high. If you shift by 2, it will be still quite high by a little lower. And then you will have a certain separation in which effectively this autocorrelation, which is the correlation measured between the same array just shifted by a certain number of steps, will become low enough that it is negligible. That effectively you can consider 2 samples that are separated by that amount of steps as 2 independent samples in the chain. And so because the error that you make using the chain instead of the integral scales like square root of autocorrelation times divided by number of samples, this means that basically what you need to do to make sure that your chain has converged is to run a chain for a large multiple of the inverse of this number. And so if your autocorrelation time is large, this means that you need to run the chain for much longer to ensure that it has converged. But if your autocorrelation time is small, it means that you can run the chain for a shorter amount of time to obtain the same number of independent samples. The problem is that the autocorrelation time is not very easy to compute, because you need to have the whole chain before you can calculate it. And actually, on short chains, your estimate of the autocorrelation times is very unreliable. So because of that, it's very difficult to do optimization while you're running the chains. However, in general, there is somewhat of a correspondence between optimizing autocorrelation time and optimizing acceptance rate, at least in simple cases. And that's why having the acceptance rate in that sort of nice region between 1/4 and 1/2 typically means that your autocorrelation time shouldn't be terrible. Although you can't really predict them, you can only compute them after you're done with the chain. And finally, there is this issue that simple MCMC method, for example, Metropolis has here, they break in some conditions. So the most typical conditions in which they break is that if your posterior is multimodal, and especially if the 2 modes are not connected, but they're separated by a large amount, this is something that is very hard to deal with. And it's not because you don't find them. Usually you will find them as long as you ensure that you start your samplers in different areas. The problem is that it's very hard to believe that your chains, the density of points is proportional to the volume in the local minima. This is the thing that, as we will see, typically breaks. And so for that, there is no obvious solution. You have to look at a problem. There are more sophisticated sampling algorithms that can help in that case. But hopefully something you can still do is use these sanity checks and convergence check to see, at least to realize that something is going wrong. So you at least have something that tells you, hey, this is a chain that you cannot trust to get these kind of results. So please, move on to something that is more suitable for this particular situation. So this is all that I have for theory part. What do you guys think? Questions? Yes.
You kind of skipped over.
That's probably because I don't know it.
No, I'm sure you do. So in order to do all of this, you need the likelihood.
Right.
And it's often not obvious what the likelihood is, right? Then that involves the correlation matrix. I don't know, I feel like there's a lot of hidden pieces in that.
In the likelihood?
Yeah.
Yeah, it's true. And I mean, I really feel like that this is so problem dependent. So this, everything that I'm doing and, even the coding that I'm doing today somehow assumes that your likelihood is known, that you know how to write your likelihood. How to write your likelihood, I feel like this is like,
That's a separate issue.
Yeah, it's a separate issue. And I mean, yeah, definitely, you're right, something that is very worth exploring. But I also feel like it's a lot less general, right? Because I imagine that according to what your problem is, what your data is, what are the things that you don't know about your likelihood, you could go about it in many different ways. So in fact, what we are going to do today, we're not even going to use data, right? We are going to assume that your likelihood, that our target likelihood is known. And this is, I will comment a little bit on how would this change if I were to use real data. But for example, the only example that I have direct experience with is that if we were trying to fit the spectral galaxies to get their properties, what would this look like? And I imagine that this, is in common with many other problems, but also that there are other, cases in which this is not known. So actually, if you have this in mind, we can comment on this just as a reminder of, this is how you sample. How you write your likelihood is, another different big issue. Anything else that I cannot answer? Okay, great. So let's see. So now what I was hoping to do is doing a little bit of I code, you code with you guys. Are you all comfortable with a Jupyter notebook, or you can look over the shoulder?
Should we just open a blank one?
Yes.
Okay.
Yes. You can just open a blank. And we'll fill a little bit of that together. All right. So if you can open a blank, these are all actually NumPy, matplotlib.pyplot as PLT at the moment was Stevie was doing, which is empty. Matplotlib inline is all that we need. I imported MC just because I wanted to show you one function from this. This is the package in download, which is able to handle more complicated posteriors than we have. But for us, these things are all that we need. So as long as we are here, we're good. You can import NumPy, you can import matplotlib.pyplot as PLT, and you can do this just to show the figures without having to type plt.show every time. Okay? And so as we mentioned, the simplest MCMC code requires these three pieces. One is the likelihood, big deal, but for us we're going to assume that we know it, and priors, so that you can evaluate the posterior H point. Then, as we know, we need a way of knowing where to go next, which is the proposal density. Right? This is how we take a step from one place to the next. And then finally, we need some criterion to decide whether the step is accepted or rejected. And what we use in Metropolis hashtags is what we just saw in the slide, and what we will use to build our timestamp. Are we done with the imports? Yes?
Do we need to have MC installed on our?
No.
No. Okay.
Yeah, no, I put it actually optional, so if you have it, it's good, but if you don't, it doesn't matter. Okay, and so as you can see here, so I'm going to define a 1D likelihood function, and guess what? I'm gonna make it a Gaussian. And in some sense, I'm sort of like following Hogg's paper. He had some proposed problems, and so I wanted to sort of like have it so that if you go back and look at the paper, and then you can see that you're solving some of these problems, and maybe if you like, at some point you can continue and do some other ones that you don't get. Okay, so I'm writing a function. I'm saying, okay, I'm defining this likelihood, which will be like it's a 1D likelihood, and it will be a function of mu, the mean, and variance. So let's see, this should return, and you guys can type with me or even like tell me what to do. Then I need 1 over and be the square root of 2 times pi times, okay, so this is the variance, so I can put it in the square root. Okay, and then I have n p of x negative, and then I have x minus the mean, divided, squared, divided by the variance, and I think here I have a factor 2. Does this look right? 1 over square root of 2 pi times the variance, so I have this equal to sigma, and then exponential negative x minus the mean divided by 2 times the variance. Yes? Approved?
Is the variance b squared?
Well, it's the variance, not the standard deviation,
okay,
so
okay.
yes, it's already square. Yeah, it's a little confusing, but yeah. This is what Hogg had, and so I didn't change it, but yeah. If you had sigma, this would be sigma. Okay, so we can plot it also. So I'm going to do points, let's see. Now pi dot linspace, negative pi, so 5, and then 100. Plot point, and then let's give it a mean and a variance. And again, I think like in the paper he has 2 and 2, and so if you want to like keep following it, so we can look at the pictures and make sure that they're the same, we can do the same. Oh, what did I do? Oh, I didn't do my own input. Confused by the microscope because this was like not executed. Okay. So this looks a little familiar. Are we good so far? We have our likelihood. So all you need is to have this formula. I mean, actually, normalization is not even that crucial, but as long as you have this likelihood, you have like piece number 1. Actually, for now, we can forget the priors. We'll put them in a moment, but just to keep it simple, let's assume that we have like some like flat proper priors that extend all over the region that we expect. So this is our likelihood. Okay. Then the other piece that we need is a proposal density. And guess what that would be? Another Gaussian! Yes, we love those Gaussians. I mean, but the proposal density is actually kind of okay. And so I called it try 1. And in general, the proposal density will be centered at the point where we are. You don't want to center it somewhere else because this doesn't make too much sense. So typically, it will be like centered where you are, and then it will have like a certain standard deviation or variance that tells you how far away typically you will go. And so here in 1 dimension, I'm going to say, okay, this proposal density should return. You can use this function, numpy.rand. This generates a random number but the fact that it's an n here means that it's distributed like a Gaussian, and so I think these will have x plus sigma x. So this is a distribution with 0 mean and 1 standard deviation.
So you're using a Gaussian sampler to build a Gaussian sampler.
Right. Well, I'm using a Gaussian. Well, the proposal density is like it's a Gaussian. This is fine, actually. It doesn't matter. What I'm doing that is actually not usually the case is like I'm using a Gaussian likelihood. So what I'm saying is here, like my likelihood is directly proportional to the parameters with that. So this is the unusual thing. The proposal density is actually reasonable. Assuming that the likelihood is a Gaussian with known mean invariance is like a big simplification. Okay, so this also, I think is correct. I have my cheat sheet here. Yes. The look, I don't know. Okay, all right, and so we have this function. And so basically, now that we have the likelihood and we're ignoring the priors, and we have our proposal density, I'm gonna say, let's give like 10 minutes and try to build a Metropolis aspect, just because it's fun to do. So this is the pseudocode, where you can initialize the value of the independent variable, some location, for example, 0, right? It doesn't really matter too much, but you want to be somewhere that's like not too far from when you're supposed to go. And then, if you want to create an object that contains the steps that you take, the chain, you will probably need to initialize it to be like a list on an array. And then you have to repeat these things for n step times. You generate a uniform random number between 0 and 1. And so the simplest function to use is random.rand. And you have to put a default value, so it will give you one random number. Then you generate a new point starting from x using the proposal density that we wrote with sigma equal 1. Right? It has an argument sigma, and then you can calculate the posterior p of y and p of x using the likelihood function we defined, using mu equal 2 and sigma equal 2. Actually, variance equal 2, right? This is unfavorable. Let me fix it. That's not the same thing. La, 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 la. Okay, so priors would go here, but we are ignoring them for the moment, so we're just going to leave them out. And then, if you found that the posterior y is larger than r, accept step. Otherwise, you will reject it and we'll write the whole step to the chain. And so notice that because r is a number between 0 and 1, this means that if your new posterior is larger than your old posterior, you always accept. And if not, you will do this game where you're like only accepting if the posterior ratio is larger than the reference number we have generated. So let's see. We can work at this for a little bit. If you need help, I'm happy to help, and I think there's also other people mentioned that they've done it before. They can help.
Oh, okay.
When you call NP, is that generates one? I'm using the line. I'm just trying to do it.
If it is rejected, it will still the
Right,
code doesn't
old,
Zero.
change the old
so the old value if the rejection is happening, do you store repeat that value again and again?
Yeah. If it happens a million times, it's possible that you are in place and it's not rejected by your priors, and that is much more likely to cloud. But yeah, the idea is that you repeat as many times as necessary to
Yeah, so you repeat, but during the time you repeat,
Yeah, we can zero
count
there is
them,
one.
Yes.
count these like
Yes, because this is how you ensure that you stay a lot of times, so you write a lot of points, so you have a high density in the region that have a high posterior. Because it's unlikely that you will find, it's unlikely to But here you have everything full screen. So let me move it. I can help? Yeah. Sorry, mind. I'm making it bigger. I wanted to make it bigger, but I figured I don't know if you guys wanted to have likelihood and proposal distributions on screen. Are you both okay with this? Yeah, okay. Then I'll make it bigger. Thank you. This works?
Okay. Wait, do we predefine the what? I think so. Should we like should we do that? Oh, yeah. How many do we need?
Anybody?
Okay, we'll do
else?
that. Happy New Year. They're on the point. I don't know.
Oh, sorry.
First you said special.
Step two at work.
Step two's easy.
Anybody's done? Okay. You, shall we give it another minute or two? That's it?
Oh, it's just
My problem is I can't see that and the
Right.
screen at the same time.
oh wait, oh it's that's the.
This is a problem for old people, Vivi.
Well,
You didn't think about that.
This is one.
no, but I simplified your
I don't know, I need to break out and get bifocals, but I refuse. Okay, so we. Also.
Sure, that will get you through as the guy, just give you.
Now, okay, now you're putting the likelihood.
Or like, yeah, this one. It's just like.
Yeah.
No, that's for the.
That's the random number. So I,
Oh, yeah, that's for.
do you sure that's right? Yeah.
We literally just put it into the. Yes.
You choose that.
No, I mean, yeah, it's just the L that we find is just the custom. Oh, right. Okay. Yeah, well, because that's what you use. So you can like
Oh, there is inside there, look it up.
Oh, yeah.
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 Okay. Okay. Put a low and high.
Yeah, it's whatever.
Right, in 1 minute, I'm gonna show you.
Do we block the gene?
Say again?
To check our code, do we block the gene?
Yeah. You can plot the samples. You can plot like the most useful thing that you do is you plot the histograms of the samples. Ideally, because we know that our posterior density functions, they should look the same. So we're gonna look. Right, yeah, guys, I'm gonna show you what I have, and of course, this is not the only way to implement this. So this is my initialization. I'm saying, okay, initial point is 0. Accept equals 0, like I want to track the acceptance rate. This doesn't matter now, but it will. Right? And so this is, I'm justifying this is just a list that will contain my sample. Okay? So now I'm saying, okay, I'm going to use 10,000 steps. So, I'm repeating this a bunch of times. I'm generating my uniform random number. Then I'm saying, okay, y, which is my new point, is my proposal density centered at the current location with the standard deviation of 1. Then I'm saying, okay, if the likelihood, this really should be the posterior. We are missing the prior piece, but that's okay for now. If the prior at the new location, if the likelihood at the new location divided by the one at the old location is greater than my random number, then now I will update the location to be y, and I will increase my current count of the accepted steps. This is something I didn't ask you to do, I'm just doing it for myself. And then, in either case, I'm going to append the point x, which is my new current location, which is either the same as the old one if the step has not been accepted, or the new proposed location if the sample has been accepted. So hopefully you had something that looked more or less like this, maybe better, I don't know. So now, how can we make sure that this works? Well, the simplest thing that we can do is to plot a histogram of the samples. Because, of course, here we know that the posterior race should be a Gaussian with the mean of 2 and the standard deviation of 2. So let's see. And let's see if this equal 100, so it looks a little bit nicer. And I'm going to say normed equal true. Since I'm hoping to recover a posterior, the histograms want to be normalized so that the area is 1. And then I should overplot my likelihood in this case, because I put no priors, and so I still have my points. And then now points to 2. Oh, I didn't run my sheet. So by the way, so I got an acceptance rate of about 78%. Is this good or bad? Yeah, it's not great. This should be more like, for like optimal sampling, it should definitely be something like less than 1/2. We want the measure. It's not this simple, probably not a big deal. But this means that in general, should I make my proposal density bigger or smaller? If I want to decrease the acceptance rate, bigger. I want to actually typically go farther. And so we will see these, but in general, I should multiply these by a larger number. Anyway, here, let's see if now this is done. Okay, of course it's a simple problem, but this is the magic. You see how simple the algorithm is, right? It's literally a couple of lines. And of course this is a simple problem, but it actually works in several cases, really. If you have like no pathological issues, like very separating multimodal distribution, this works quite well. And so you have your histograms of, it tells you about the locations that you visited and how often, and this is how the likelihood, which is our fake posterior, because we are neglecting the priors. You guys good so far? You have your samples?
So the acceptance rate, I mean, what does it mean by the acceptance rate? It means that
The acceptance rate is like how many times, I kept track of how many times, how often a step was accepted when proposed. And so this means that in 78%
Oh my god.
of the total steps that were 10,000, the new point was accepted.
Okay.
And this is too large, usually, to have effective sample. So this means that I'm not moving enough in parameter space. Which doesn't matter, as you can see with this problem. But if the problem is more complicated, this mobility is too low, and I should aim for moving more, which means that I will accept fewer steps, but I will explore more efficiently.
so that means about 20% of the time the point would not move, right? Is that
No, actually, yes, exactly. yeah.
When they don't move, that means that they repeat their.
Yes, 20% repeat. Yeah.
So that would be you have several samples that have exact the same
Yes,
value of.
Yeah, a few samples that have exactly the same locations, which is fine.
Okay.
Yeah, because
Yeah.
this is what makes the density be high in this good region.
Yeah, but I'm just imagining if you sampling from like a random, like a Gaussian
Yeah.
likelihood, how likely is that you have several samples that have exactly the same value when you repeat?
Right.
This will be exactly the same. Just
Right,
feel like
but keep
it's,
in mind that in the end they're always, because you're always sort of like putting into a histogram, and so several locations, like nearby locations, effectively become the same anyway.
Okay.
But here, yes, I think we could try, which I wanted to do later, but even then we don't have that much time. You can see that. So if you put 2 here to make our proposal density larger, you can see that the acceptance rate is down. Right, and so this is like the simplest thing that you can move around. For example, if I make the standard deviation of the proposal density 5, now I get an acceptance rate of 33%, which is probably closer to where I want to be. And this is how my samples. Okay, I'm going to move on to see if we can get to like the next thing. So problem 3 in Hogg's paper was the same exercise, but with like a uniform likelihood. Look like that, and so this is
that one part.
think she's using
to see what happens.
this out as a
So you can see that in this case, what is happening. So I basically run the same code, but now with a uniform likelihood. You can see that my samples resemble my uniform likelihood. Notice that since I had started at 0, but this likelihood was defined to be between 3 and 7, my chain had to spend a little bit of time here before it could take a step large enough to move in this region. But still it happened, right? So no hope is lost, and this is not bad at all. And sometimes there is like this initial part of the chain where the chain is sort of like, trying to find its way. It's called bird-in, and some practitioners recommend that you actually get rid of that initial part as, like your code is exploring the parameter space. But really, if your chains are run for long enough, this shouldn't matter. So that's why actually it's not a uniform recommendation. Okay, now, another thing that is kind of nice to do is using log-like rather than the likelihood. This is just because, this is like an exponential negative Gaussian, so this is not like a real argument, it's more like, for numerical reason, usually using the log of the like is a bit more stable. And so typically this is what is done. And we can add priors, and so we can add flat priors. And here, like I put some numbers between 0 and 4, but you can be whatever they are, just to see what happens. And so here, the thing that I wanted to mention is that x for us is our parameter, right? It's the only dimension that we have in parameter space. So normally, the likelihood depends on the parameters and on the data. So in a real-world case, what would go here, this likelihood wouldn't just be like a Gaussian in x, u, and the variance. It would be, for example, for me, if I'm observing a galaxy spectrum, well, the first bit, I would write it as a Gaussian, but the first bit would be my what my spectrum would look like as a function of the parameters. So there will be like a very complicated function of the parameters that generates the thing that you believe would look like how your observed points look like if the parameters were correct. And then you will be comparing this to your observations. And so that would be the bit that is called mu there, that is now described as observation that only takes exactly the average value of the likelihood. In real life, you have like a series of observational data points, and each data point will come with some uncertainty, which will take the place of this. And so this is, in general, for us, it's like a simple Gaussian function, not even just of a function of parameters, but just of like the only parameter that we have. In reality, this is the bit that is much more complicated. But for me, I'm just defining a log-like, so it's the same as before. So I'm just going to take this likelihood. It's too lazy even to type it again. Okay. So now I'm going to say, okay, the log, so I can take the log of the constant. Right? And then I'm going to add this bit. I get rid of the exponential part. This should work like a log of a product sum of the two. And then I'm going to define my priors. So now what do I want to do here? Basically I want to say if for flat priors, if x is in between the low and high limit, what should this function return? Flat prior, if I'm within the priors range, what should this function return?
1,
1, but it's a log, so
0.
0. Otherwise, what's the log of 0?
Negative u.
Sad, but actually, I think it's, I can't remember if it's a function. So yeah, don't blah 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 blah. Okay, so this is what my priors look like. And so now, like I can do the same thing that we have done, but a bit more proper because we also have a prior bit. And in general, your prior may be different from here, but at least, it's good to put them in place. Now, one thing I want to comment is that using log-like and log priors as variables is very different from using log x as a sampling variable. There are many cases in which, for example, again, with me, I was looking for like masses of galaxies. And it's usually much more efficient to sample using log mass as a variable rather than just a mass, just because these things tend to span many orders of magnitude. So this is, has nothing to do with what we're doing here. This just means that my acceptance criterion will be expressed in terms of log-like and log priors. So I also will have to take the log of my random number, and then I will look not at the ratio of the posteriors, but basically at their difference, if you will. But that's one thing. If I were to switch the sampling variable to log x, this is still legit, but this is like basically a change of variable in your integral, and this carries the Jacobian of the transformation. Or in one dimension, as what we're doing, basically you'll be integrating not in x, but in the log x, and this carries an additional 1 over x. So this is just something to keep in mind, that using log-like is very trivial, but if you're actually changing the sampling variable, then your priors becomes modified with like an additional factor, which is the Jacobian of the transformation, or really in one dimension like this, with a factor that is just like the derivative of the new variable with respect to the old variable. Probably was obvious to all of you. Okay, so now I'm gonna grab my old algorithm, and now I'm gonna rewrite this. Actually, I want to go up here, yes. I'm going to rewrite this, but using log-like and adding the priors in a little bit nicer. Okay, so this is still the same part. Here I don't have to do anything. So here, what I want to do is, rather than L, the likelihood, did I call this function? Ln like. Okay, and then I'm going to add my prior, Ln priors, right? And then I'm going to subtract Ln like of the old point and Ln priors of the old point. And then I'm comparing not to just a random number, but I have to take the log of. Okay, hopefully this works. All I have done is that I'm using log like and I added my priors here. And so they are, because I'm working in log, they add rather than multiply. Looks good. Shall I run? Okay, so my acceptance rate is now at 25%. I have to make it bigger. Let's make it subdivision 4, okay? And let's take a look at the samples. I'm just going to look at them again. How do we expect that these samples will be distributed? Any idea? Do they look like a Gaussian? Yeah, no, maybe. Don't be shy. Am I working with the Gaussian likelihood? Yes. How are my priors? Flat. So all in all, hopefully, oh no, go away. So see, they're still Gaussian, but notice that now I have implemented my priors. So actually, it's kind of easier to see. Hey. Yeah, thank you. Yeah, I could have put range here. So here you can still see that, like they resemble the Gaussian distribution we're drawn for, but because I also have priors, then the priors have basically limited the range, which is what we expect, right? So it's all good. In the end, your posterior depends both on your likelihood and your priors. Okay, so the next thing that I think would be nice to do is to try and look at this in 2 dimensions rather than 1. This is incidentally problem 4 in Hogg's paper, just so because once you move away from 1 dimension, then you can go in as many dimensions as you want. Because as you can see, the main difference between having like a likelihood in 1 dimension and moving on like 2 or more is that your standard deviation / variance now becomes a tensor. But once you've done it for 2D, you can do it for any dimension, so I think like it's a neat thing to do. So this is how my Gaussian likelihood in several dimensions will look like. So I'm going to try to write it, and you guys can check as I go. Oh, so I still want to, I'm going to do first the likelihood and then take the log, because I don't think I can handle both at the same time. All right, so I'm going to do 1 over. Okay. I don't need square root. 2 times pi, the power of, I'm going to call it n. This is the argument I put for myself. Divided by 2 times. Okay, so now if I have the covariance matrix, then this would be pi dot lin alg. That's like the linear algebra modulus in Python. And then I just do that. Of map, and then I have an pi dot x, and here let me put the -1/2. Actually, I'm going to break it in 2 lines. phi dot. Then like another phi dot is okay. Hopefully this works. And so now I'm just gonna take the same thing and take the log.
I think that the bracket for the covariant matrix in the denominator.
Here, this.
Yeah, this
Um,
been,
Oh, well, I need to, yeah, I think, yeah, I'm pretty sure that this is some symbol for the determinant of that.
right, basically in the denominator, no?
Here?
Right.
Here?
No, the one,
Here?
yeah, this one.
Yeah,
Should this one be in the denominator?
let me see. Divide by, yes, that's right. And actually, I also need to raise it to 5.
Alright.
Thank you. Okay. Copy it again. Okay, and so now I can take log of this. Let me see. If it looks like, so what I did is like, okay, I have this part, figure out if I made a mistake.
In the first one, you're taking an exponential of -0.5. Well,
Oh, that's definitely not something. And so here I finally go read the So now I give the covariant matrix that again comes from the paper. And let's see if it's loaded. Just define it like read the values. And let's see if the surface looks blackish. Yeah. Okay. The 2D Gaussian. So this is all that I done, like basically I have used this like multi-dimensional likelihood set to the 0 using the covariance matrix that was defined in the paper. And this is how it looks like. Okay, you guys have this one?
With those, yeah.
Yeah?
But not the next.
Yeah, this one, no. This was just a little checking. You guys have the multidimensional likelihood? Okay. Okay. We can also update our priors to be multidimensional. And I'm sure that this is like a terrible way of doing this, because basically this means that in one dimension this is still required to be like an array list of some sort, but I just couldn't figure out how to do it quickly so that it works for all dimensions. But this is basically something where I have like flat priors, where here I will need to define what those priors are. And this is just checking that for every dimension it's true that the value of my array is comprised between these two. So if you want to get that, then we can try to work out to the 2D problem. And then actually, what would be a great idea, but I was too lazy to do it, is define 0 + 0 function. So that actually, rather than calling them separately, you have a call only one function that will combine your values and you have 0 for the new point and for the old. I didn't do it, but it's probably a good idea. state our code to be a 2D sampler. So you have your Marginal Likelihood function, where this is the mean and this is the covariance, and you have as proposal density. This problem 4 in the paper. You can use the 2D identity matrix and use flat priors in all parameters with a range of -10 to 10. Yeah.
Can you just zoom out?
Out?
Oh, yeah.
Oh, so you can you look at this one.
Yeah.
So since we don't have that much time left, we can either work on this thing, or if you want, I can just move on to the solutions, and we can look at things like how would you check the convergence and what happens when the X break. Shall we do that? Okay. So let's assume that we've all solved this problem. And this is my solution, which, as you can imagine, is actually not that different. Right? The idea is still very similar. You're now initializing here, and then your proposal density is now multivariate normal. And here you're specifying what its covariance would be. And this is just means like how many random samples you're generating. And then these are my posteriors, which are the product of the multidimensional log L. Actually, they are the sum because they're a lot, and the priors, and this is where the priors are specified. And then I'm just implementing the same criteria of saying, okay, if this is satisfied, then my new sample will be the new point, and if not, then my new sample will be the old point. Okay, so I'll leave it there, and I put all this on GitHub so you can also take a look. Okay, so let's say, what did I do? Okay, so one thing that we can do, okay, our acceptance rate is a little bit higher, which means that you can do it with the proposal density a little bit. This is how the samples are distributed now in 2D, and this is how they're expected to be distributed. So now that I have these, right, and this is in general, if you're writing your own thing, what you want to do is, okay, what can I do to make sure that things are working as expected? So that's why I'm calling it sanity check. So the first thing is like, we should see what happens if we make the likelihood very small. So, if you're working with the likelihood, you could raise it to a tiny power. If you're working with log like, you could just multiply that piece by a very small number. What should happen in this case? What should I find when I plot my samples? If my likelihood is tiny, which piece will dominate? The posterior. What's the other piece? The priors. And so this is like, a good sanity check. If you make your likelihood tiny, you should find the shape of the priors. It's easy to do, but this tells you, in case something is going wrong, this is something that is easy to do. So here, for example, here I can go here and I can multiply just this bit by 0.01. And then I will plot the samples again and see what happens. Okay, you can see also that I have a very large acceptance rate. That's not, does this make sense? Yeah, because if I'm dominated by the prior piece and the priors are flat, this means that it's very easy to move to good places. Basically what I'm saying is like, every place is the same, and the ones that are rejected are probably because I'm going out of the region that is allowed by the priors. So if I do this, here you go. Right? And this is also, notice that this is not like an equal plot, so the range is the same. It just looks very rectangular, but really it's a square. And so this is like a good thing. Okay, next thing to check. The other one is we can check what happens, and in a way we've done this already, when we make the proposal density very small or very big. And this should affect the acceptance rate. So if I make the proposal density tiny, what happens? Acceptance rate goes up. Right? That's the whole idea. And so how can I go in here and make my proposal density small? Where is my proposal then? Which function here is the proposal density? It's taking me how to take a new step. It's telling me how to take a new step. Any ideas of where that is? Is it here? No. Is it here? Is it here? Yeah, very good. So here, if I take this, at the moment it's the identity matrix, and I make it tiny. Then you can see that my acceptance rate has now jumped at 91%. Vice versa, if I make it big, I expect that the acceptance rate will be smaller because it's much easier to go outside of the interesting area. And so you can see that here it's at 20%. So this is another thing where, if there is a bug in the code, these are like two easy way of spotting it. And so this also means that probably, I don't know, my guess is like I want to be at something like 3. Yeah, this gives me an acceptance rate of 40% that actually in 2 dimensions is actually quite good. So moving on. Another thing that I can do is to look at this thing called the trace plot. And so in this case, I'm just looking at the first parameter, and index 0, and I want to see basically as I was moving in the chain what that parameter was doing. Now what is expected to be doing? And the idea, should this parameter stay always at the same value, so to go up and down? Right, the value of a sampled parameter, should it go up and down, should it stay at the same value? What do we want in a healthy chain? Up and down, right? You want basically your parameters, what we call is like to traverse the parameter space several times. If it's stuck, that's not a good sign because it means that your chain is not a chain that has sufficient mobility to be reliable. And so here you can see that this is moving up and down. Its range, as we remember, is roughly between like -2 and 2, but it's actually like moving around. And so this is healthy. Again, is this like, the final seal that your chain works? No, but these are all things that, should look like this before you can proceed further. And so at least this like, basic sanity check we have passed.
There's that transient period at the beginning, right? Like,
There should be. I don't know if I have where I have these things. So this is kind of neat to do. Let me see if I have something I can copy here. I had it further down. So yeah, this is how it looked like. And then usually, if you put like a point a little further out, you would see like behave like this. But typically, just because this is such an easy case, that this is really tiny, and so it's hard to see it in a trace plot. In a more complicated problem, you would see that sort of, like initial period of like wandering around, and it would be like more obvious even in a trace plot. Here, probably this burning phase, this is like, I think I was plotting like 100 steps, and so you can see that probably like within 20 or so, it has already converged, so you wouldn't see it from the plot.
So I guess you'd see the fluctuations increase as you go along, as you move out of this transient period.
You would need this transition. I mean, like what you would see is like in the very beginning, you may see like, a larger fluctuations because, if your priors are large, then, you could be like very far from where you're supposed to be. And then once the chain is sort of like a stationary distribution, you will see basically like moving up and down in like a relative, in the interesting region. The important thing is that it's not stuck in like
When you're really far up, it looks more like an optimizer, right? Because if you're really far out, then your steps are...
In this first part, it almost behaves like gradient descent. And but then as soon as this is done, then it starts like really sampling. And so like the part where it goes up and down, this is sampling, but yeah, you hardly ever end up in that area, which is like very far at 0 to 0. Okay, so now convergence. This is something that we have mentioned, and to check that the chain is converged, you can do a couple of things. If you have only one chain, the thing to do is like you can break it in different pieces, and you can check that when, for example, you calculate things like your average, right, your mean, or your credible interval, so they look the same for every piece of the chain. This means that the distribution associated to the chain is stationary, which is a good thing. And so here, for example, I've defined this function that splits my chain in 4, and then plots like the mean and the standard deviation of the parameters for each quartile of the chain. And you can see that, these are like just 2 parameters, but you can see that they look the same within the standard deviation. So this is like, another good thing. It's actually more interesting to do this, or in general, like more wise to do this with multiple chains. Because as we mentioned, the initial location may matter, and so this is something that you can only really explore if you have several walkers that start at very separated area of the parameter space. In fact, you may think that you want to start them at random location, but actually my take is like farther away from one another, the better. So if you have like, in general, that you want to make sure that they sort of like cover a large area in terms of initial locations. And then when you want to find things like the mean, the mode, the credible intervals, all that you have to do is to look at things like here. For the mean. This is for the 2 parameters. So all that I'm doing is looking at the 50th percentile for the 50th percentile for the median, and then the 16th and 84th percentile to define my 68% credible interval. And so as I mentioned, I like it to do it coming in from like 0 to 16, coming out from 100 to 84, so that you're not anchored to central value, which you don't know if you can do. And for 95, you do the same thing with 2.5 and 97.5. Right? And so this is, I feel like, the part where you're not doing any integration, you're literally just counting how many samples you have.
You also know the mean, you still have to calculate it.
Right, but still, you're just going to calculate the mean of a certain functions. You can take all the points and you can basically just average the value of that function or parameter over all the points. So yeah, it's like, you will sum and then divide. So yes, it's, you don't do it this way, but it's still super easy. All right, guys, so this is just something where, that I wrote to run multiple chains. So maybe I can show you this one last thing. And I want to say this is very poorly written because I really should pass the posterior as an argument to this function. But I was a little bit lazy. So yeah, it is. But all I'm doing is like, I'm adding a wrap to the state. Okay, now I have 4 chains. And I mean, if I don't specify where to start, they will all start at zeros, which is a terrible idea, but it provides something. It's 2 dimensions, and I'm taking like 10,000 steps for each. And then everything else is the same. It's just that my samples, they used to have only 2 dimensions, which is the number of steps and the number of parameters. Now it has the 3rd dimension, which is the number of chains. And in general, it's a good idea to have 4. And so now I can run it, and let's see, my priors are between -10 and 10. So I'm starting at 0, 0, 9, 9, -1, -2, and 3, 2. Is this like a good set of starting values? Zero, 0, 9, 9, -1, 2, 2, 3. Not terrible, but actually it would be better if I spread it out. So again, we're working with a very simple problem, and so probably in the end it will not matter. But as practice, this is probably not the best idea.
How do you know how far to spread them?
I would just like spread them out as far as possible. Like, I mean, actually, it's not a trigger problem. The one of like, given like n parameters, what's the best possible distribution to sample? But you can find something like I would what I used to do when I like wrote my own is like, I would like put it somewhere, somewhat closer to like the kernel parameter space as long as. But I mean, there are different ways.
So does it depend on the characteristic scale of your system?
So again?
Does it depend on the scale of your system?
Well, I would say on like, the volume of parameter space that reasonably you can expect to explore. I would say that you want to have like a decent coverage.
You could just put the starting point at the corner of your parameter space?
I think for many things it works. The only thing is that, if a corner is so isolated that the chain actually never reaches the interesting region close enough, this may cost you a lot in terms of computing many steps. Okay, so this is, here you can see the path of the one that started at 9.9, but you can see that in this case it's quickly went towards its destination. And this, you can see that for two different chains, the distribution actually converges other than this initial burn-in phase, chain number 2, which was the one that started like outside of the range where the posterior is held. And so here, we are looping over the chains, looking at parameter 1, and we can look at the estimates that we get. And so you see, like for the 4 chains, the medians are slightly different. This is okay, because again, MCMC is not great as an optimizer. And so like any single point statistics that you quote is never going to be great, right? There is no guarantee that that median is like, the most significant thing that you can say. You always work in terms of credible interval, and then you can give like an estimate of, hey, this is the median, but keeping in mind that the median is not the mode, it doesn't have this sort of like, particularly special states. So when you look at the 68%, 95% interval, you can see that, there are some fluctuations, but here they're to within 10%. And then you can decide, like there are some criteria like Galban and Robin statistics, for example, to sort of like give you an idea of, is this good enough, or should you run the chains for longer in order to get even better agreement? Okay, I guess we are out of time. Do you guys want to see this autocorrelation time and or how to break? It's up to you. I'm happy to stay a little longer, but at the same time, I don't want to take too much of your time. So.
Is this notebook going to be available?
Yes. Okay. I mean, it's up to you. I don't know if, So.
Could you go over it and maybe someone who needs to name can be?
Can you say that
Do you
again?
mind going over it and people who need to name can?
Yes, of course. Feel free to leave and I will go over it if I may. Okay, so what I was mentioning is that one thing that measures the efficiency of your sample is the autocorrelation. And Dan from MIT, he has like a really nice blog post that uses some expensive statistics. What I did here is like I wanted to keep it as simple as possible, just like so you see that there is no mystery in autocorrelation time and how you calculate it. So literally, I'm using this, I'm defining this autocorrelation function, and this is defined as calculating the correlation distribution between an array and itself. And this function just works like, actually starts like at a very large negative number. So you first you shift the array by large negative number, and then left, then you go to 0. At 0 you have the maximum of that. You normalize with 1, and then shift. So just because of the way that this function works, I have to take the second part of the array, because I want to start at 0 and look at what happens as I shift by a positive amount. And then I'm normalizing by dividing by like the first term, which is like the value of the function is 0. And so this is like for my chains, for one of the parameters, actually the second parameter, parameter 1, that's really the same. I'm plugging it. And you can see how it looks like. Remember that this is a very simple problem. So you can see, of course, the autocorrelation being 1 when the lag is 0, is 0, right? And then it decreases pretty quickly. And you can see that probably, like once you reach this number like 20-ish or so, This means that your samples that are separated by 20 steps or more, are truly independent samples. This is a pretty good number, right? Now you know that your error in the estimates that you make when you use the chain instead of doing the full integral of the posterior is proportional to square root of this number divided by the number of samples. And so this means that with 10,000 steps, if the autocorrelation time is 20, then you have 500 independent samples, which is a decent number. You have this number, you found 100, 200, 300, then it means that you will need to run the chain 5, 10, 20 times longer to obtain the same number of independent samples, which is why I feel like they claim pretty strongly that autocorrelation time is the best measure of efficiency. Now, if you don't want to plot it, MC, and this is like the only MC thing that I'm doing, has this function, it's called autocorrelation integrated time. And so if you run it on exactly the same, but this is actually for only one of the chain, for like the second chain. So let's see, for the first, you get 17. For the second, 18. For the third, 34. I guess this is probably the red one. And for the fourth is 15. And so this is a function that I put here because I feel like it's handy to use. If you don't want to do the plot, you can use it and get an idea of how many samples you need to get through two independent samples. Now, what do you do with it? We used to thin the chains, right? So there is like a notion that if you want to provide truly independent samples, then this means that you are only allowed to take one every autocorrelation time samples. And so if this is your goal, this is one way to do it. However, when you report things like statistics, I don't believe it really matters, and I think you can count the chains as long as you have them first. And then the last thing I wanted to show you is like what happens when your likelihood is not so nice. And so here, for example, you have a double. Okay? And so here I'm running the same thing, but rather than having only a single likelihood, now I have the sum of these two Gaussian as my likelihood with the same priors as before. So this is where I'm running, and so like it takes a moment. Okay, it's done. You see that these acceptance rates are too high, and we'll see in a moment that once we fix these, things improve. But this is the distribution of my samples. So let's see what is happening here. Actually, it's like too good to be true. Usually. Right, so you can see like, this is actually like not bad, and I can't quite see the numbers too well. But okay, so this is actually not terrible, because what happened is that, okay, basically two chains found one, two chains found the other. In the end, if I took like the sum of these four chains, it would probably give me like a decent results, but this is not what usually happens. However, when you look at the derived parameters from each of the four chains, you can see that they are completely different from each other. So the good news here is that at least you get an idea that, like maybe not everything is rosy. Now let's see what happens if I make a larger proposal density, which means that now, my acceptance rate, I know that they are high, and so, like I'm trying to adjust it to getting them closer to where they would like to be. And so we can look again at these distributions and shift. So this is a typical problem. So this is a more typical scenario. Now you see that basically I believe that all the chains found the two peaks. This is because having a larger proposal density means that I'm increasing mobility, which is a good thing, right? And so now all the four chains are aware of the fact that there are like, two modes of the posterior. However, you see that something that is important for me is that the volume contained in the histograms is proportional to the volume in the posterior. And this is something that is not happening here. So I get, I get the information, that there are two areas that are interesting, and thanks to this better mixing, which means higher efficiency, now all the chains get to explore both modes, and the shift is just because like I'm shifting in plotting because I couldn't see what was what. So they're actually in the right place. But if I were to combine the chains, well, I would see that like I would derive that there is like more volume in this mode of the posterior than it is here, which is actually not true. Like originally the posterior at the same volume. And so this is a chain that is like, deeply non-converging and something that I cannot trust. And so we can look at the statistics I derive from here. And you see here that the scary part is that because these are mixing decently enough, if I just look at credible intervals, these are not terrible. And actually, these are not terrible because they're not informative. The fact that the medians are very different, well, this doesn't mean much because the median is really, like where that 50% lies. And so it's not really a great indicator of anything. So if I didn't know what my probability or my likelihood looked like, and I'm given these, this is not horrible because the fact that I'm getting these huge credible intervals tells me, hey, you haven't measured anything. But, hopefully this is, at least I get a sign that this is a problem that Metropolis Hastings cannot handle very well. And as you see, like the most common issue that I get is that even if you discover multiple nodes, you cannot trust that the volume in your samples is the same as the volume in the posterior. And so for things like these, you want to switch to something which is a bit more sophisticated. So for example, MC, I think that is engineering to deal with multimodal issues better. Nested sampling is another thing that people use to solve this sort of like problematic likelihood. So I feel like, you can always start from the simple one, and then, at least with this series of sanity checks and convergence tests, you can get an idea that you have a problem, and then you can, solve. This is actually this sort of like, dual likelihood like separated is not hugely common in many problems, but there are cases in which you have it. That the general. Right. Oh, I guess maybe they need the room. Anyway, do you guys have any questions? All right. Well, thank you so much for staying. Oops. I'll put this on GitHub.